Okay, so right. So I guess I'll talk for about half an hour, and then we'll just open this for a discussion. So I was discussing this kind of discrete braiding protocol where instead of moving the anyons around in real space, what you do is you change parameters in some abstract space of Hamiltonians, and you go adiabatically through a closed path in this Hamiltonian space, and what you get at the end is essentially the same as braiding. So I've described actually explicitly what this protocol is. It was made out of these three steps. So here's step 1, step 2, and step 3. We wanted to braid two Majoranas 1 and 2, and in order to do that, it turns out that we have to introduce two auxiliary Majoranas 3 and 4, and we don't want to get any extra ground state degeneracy. The ground state degeneracy has to be twofold throughout the whole process. So we couple 3 and 4 to begin with, and also at the end. Okay, there's a coupling J3,4, which is non-zero, such that the two extra states that we add to the Hilbert space by introducing 3 and 4 actually have a finite energy. Okay, and then what we do is this process. We turn on the coupling J13 and turn J34 off, and then we turn J32 on, and while doing that, turn 1,3 off, and then finally turn 3,4 back on. And by the end of this process, we return to the original Hamiltonian. Okay, and let me give you a motivation to why this cycle in parameter space is essentially the same as braiding. Okay, there's a very simple argument. Well, think about it as follows. At each one of these intermediate steps, okay, so if you start here, there are actually two zero modes. There's 1 and 2. Gamma 1 and gamma 2 commute with the Hamiltonian, the Hamiltonian at time equals 0. Okay, and now you start turning on this extra coupling 1 and 3. So gamma 2 is always a zero mode throughout this process. Okay, so throughout process number 1, what happens is that gamma 2 always commutes with H. That's simply because gamma 2 doesn't appear in any term in H of t, okay, throughout this step. Now, we just spent a long time arguing that there couldn't be an isolated, a single zero mode of any system, of any sort of BDG system, and this is essentially a BDG system. So that means that at every intermediate step of this, every intermediate time of the step number 1, there has to be actually another zero mode, which in general is some linear combination of 1, 3, and 4, which also commutes with the Hamiltonian. So there has to be some gamma 1 prime, if you like, where gamma 1 prime is some linear combination of gamma 1, gamma 3, and gamma 4, which also commutes with H. Now, this is a function of time. Okay, for time 0, gamma 1 prime is just equal to gamma 1. At every intermediate time, it's some linear combination of 1, 3, and 4. And at the end of the step, it actually has to be just gamma 4. Okay, because we know that if gamma 4 is decoupled from anything else, that's actually a zero mode. So basically, what we've done here, if we trace the time evolution of the zero mode, it starts from gamma 1 and it ends up being gamma 4. So essentially, you've moved gamma 1 to gamma 4. Okay, so what we've done is equivalent to moving this one over here. Okay, and then in the second step, what we do is we start from a zero mode that lives at 2, and we turn on this coupling between 3 and 2. So 2 is not a zero mode anymore, but by the same argument, there has to be a zero mode, which is some linear combination of 1, 3, and 2. Okay, and at the end of this process, 1 is a zero mode, so that zero mode must have moved from 2 to 1. Okay, and similarly, at the last step, you start from a zero mode at 4, you end with a zero mode at 2, so 4 must have moved to 2. Okay, and if you just stare at these pictures long enough, this is like braiding, essentially, okay, because you wanted to exchange 1 and 2, so you move 1 to 4, then 2 moves to 1, and then the one that you sort of stored at 4 moves back to 2. Okay, so these two exchanged. That's kind of the pictorial way, but if you want to actually solve it and find the braiding matrix, that's also possible. Okay, it's just computing, just solving the Heisenberg equations of motion, essentially, for these operators, or finding the adiabatic evolution operator. It's like solving the time-dependent Schrödinger equation in the adiabatic limit. So I'll solve it as a Heisenberg problem. Okay, I'll solve the time-dependence of the operators. And there's a simple way of doing that, so I'll just demonstrate it for one step. Okay, so let's look at step number 1 in more detail. Okay, we can write an explicit path. So let's take h lambda, where lambda is a parameter that goes from 0 to 1. Okay, and let's write this as minus j 1 minus lambda times I gamma 3 gamma 4 plus okay, and then minus j times lambda I gamma 1 gamma 3. Okay, such that when lambda goes from 0 to 1, you go from having the 3-4 coupling on to having the 1-3 coupling on. Okay, and what you want to do is to trace the time evolution of the operator gamma 1. Okay, so what you can do is look for a zero mode, gamma of lambda, okay, which is, as we discussed, is a linear combination of the 1, 3, and 4. Okay, aj, some amplitudes, times gamma j. Okay, so and the requirement is that this is a zero mode for every intermediate step of every intermediate time in step number 1. Okay, so you just write down an equation that you require that gamma of lambda commutes with h of lambda. Okay, and from this you can solve for a1, a3, and a4, and it turns out that okay, so I won't do it. It's an easy exercise. What you get is that a3 is equal to 0, and that basically right. So minus lambda times a2 plus 1 minus lambda times a4 is equal to 0. Okay, so there's some relationship between a2 and a4 that you have to satisfy. So you see that when lambda is equal to 1, then you just get that sorry, when lambda is equal to 0, you just get that a4 is equal to 0. So that means that the zero mode has only a2, which is non-zero, which is what you sorry, this is a1, a3, step number, this is 1. Right, this is 1, 3, and 4, which are mixed. I have a typo here. Okay, so when lambda is equal to 0, a4 is equal to 0, so the zero mode lives entirely on gamma 4. And when lambda is equal to 1, it's a1, which is equal to 0, so the zero mode has moved to 4. And you can track what it does at every intermediate step. But there's another piece of information here, which is by continuity of the zero mode, you can actually tell what's the phase of the zero mode. So if you start off with a1 of lambda equals 0 being 1 and a4 being 0, Okay, so this is a choice. Okay, you can choose here a minus. That doesn't matter. But once you've chosen that, you can see that you by continuity you must have that a4 of lambda equals 1. Okay, so you require that this solution is actually continuous, and that gives you that that's equal to +1 rather than -1. Okay, and a1 of lambda equals 1 equals 0. Okay, and so this way, step by step, you can solve for the evolution of the zero mode operators. You can track what happens to them, and what you find, if you do that, is precisely the braiding rule. Okay, so you find that indeed gamma 1 goes to gamma 2, and gamma 2 goes to minus gamma 1. Okay, so this is indeed this kind of process indeed actually mimics the braiding, but you can actually do better than that. Okay, so this is just solving for the operators, for the Heisenberg evolution of the operators. You can find the unitary matrix that acts on any state in the Hilbert space. Okay, this U12. So that's just essentially that's a matter of calculating Berry phases, because it's an adiabatic process. You know that what happens when you have a adiabatic evolution is that you pick up a phase, which is the Berry phase. In this case, it's slightly more subtle because there are two degenerate states in the Hilbert space. So it's more like calculating a non-abelian Berry connection. Okay, but it's basically doing an integral essentially. Here the problem actually simplifies because you have the two states that you want to track, which are degenerate, are simply the states that have an even and odd parity. So you can, and the Hamiltonian at every intermediate time commutes with a parity operator, so that's a conserved quantity. So these two states don't mix ever with each other. All you need to do is to calculate the different Berry phases of these two states along this adiabatic path. And the difference of these Berry phases is what you want. Okay, that's we wrote this as e to the pi over 4 gamma 1 gamma 2, okay, up to some phase that we couldn't tell. So the difference between the Berry phases between the two states with fermion parity 0 and 1 is pi over 2, and that's exactly the result that you'll get. Okay, so this computation can be done explicitly. I won't do it here, okay, even though the way to do it is somewhat instructive, but this is too technical. Let me just, in this particular case of the Majorana's, there's kind of a neat geometric way to do it, so to see what the result is. So let me do that and then make some more general remarks. Okay, so as was pointed out, for this particular path and parameter space, there are actually three parameters that are active, which are the three coupling constants. Okay, so let's draw them in a three-dimensional space. This is J13, this is J23, and this is J34. Our Hamiltonian starts off here. Now, the overall magnitude of these couplings is not important. The only thing which is important is their ratios. So let's fix the radius of this space. Okay, so let's fix J13 squared plus J23 squared plus J34 squared equals J squared. Okay, so magnitude. Okay, so this is essentially motion on the surface of a sphere with a radius of J. Okay, so now notice that by construction, throughout step number 1, J23 is always 0. Okay, because we've assumed that gamma 2 is always far away during step number 1. We have some coupling J13 and some coupling J34, which are on. And we basically go from J34 to J13. Okay, so during step number 1, what we do is we go essentially from here to here. Okay, and similarly in step number 2, we start from having J13 and we turn on J23, but J34 is always 0. So we move in the plane, in the horizontal plane. We essentially move from here to there. And in the last step, we go back, right? We turn on the J34 back. J13 is always 0, and we move on this plane. Okay, so all we need to do now is to calculate the Berg phase that the two states, the two parity states. Okay, so we have a good quantum number throughout the whole evolution, which is the total parity of the system. That's gamma 1 times gamma 2 times gamma 3 times gamma 4. Okay, this is either plus 1 or minus 1. We can label our two degenerate states using this quantum number, and it's always a good quantum number, and these two states are always degenerate. They have the same dynamical phase. Their dynamical phase is exactly the same, okay, because they have the same energy throughout the whole way. However, they can have different Berg phases, and we just need to calculate the Berg phases that the two accumulate through this path. Okay, and that can also be read off from this picture in the following way. So if you think about it, you have here three terms in the Hamiltonian, which are I gamma 1, gamma 3, I gamma 2, gamma 3, and I gamma 4, if you like. Okay, I've just written it in a different order. Okay, so these three terms satisfy in algebra. The square of each one of these terms is 1, and these terms all anti-commute with each other. That's exactly the algebra of Pauli matrices. Okay, so within this 2 by 2 subspace, I can actually represent these three operators as sigma x, sigma y, and sigma z. Okay, that's the way these operators act on my two-dimensional space. Okay, and what I'm doing here is simply sweeping effectively a magnetic field in this 2 by 2 space. Okay, and I'm splitting partially the degeneracy. Within each one of the sectors, p equals plus or minus 1, I have two states that have the same parity. On this two-dimensional Hilbert space, these three operators act as Pauli matrices, and my ground state simply follows adiabatically this effective magnetic field. Okay, and then you know just from this picture how to read off the Berg phase. Okay, that's the famous problem that was solved by Berg in his original paper. Right, the Berg phase for a spin-half particle, when you change the magnetic field on the sphere, is just equal to half times the solid angle, which is traced by this arrow. Okay, now if you do the math, then this is essentially 1/8 of the solid angle of the sphere. Okay, and that we need to multiply by the area of the sphere, which is 4 pi. So that's pi over 4. Okay, so this would be the Berg phase that one of the two states accumulates, and it's not entirely obvious from this picture, but it turns out that the other state, this would be, for instance, the Berg phase that the plus 1 state, the plus 1 parity state accumulates. It's not entirely obvious from this picture, but it turns out that for the p equals minus 1 state, you just get the opposite sign for the Berg phase. Okay, the reason is that the same matrices would be represented by the same operators would also be represented by a Pauli matrix on the other parity state, but you get an extra minus here. Okay, so it's essentially like tracing. Instead, it's reflecting the J23 axis, and it's essentially tracing over this path. Okay, so the orientation of the path gets reversed, and you get minus the same phase. So this is actually plus or minus for p equals plus or minus 1. Okay, and that would give you precisely this result, because in the initial and final Hamiltonians, the total parity in the ground state sector is just gamma 1 times gamma 2 times I. Okay, so that's the discrete braiding protocol for Majoranas. Now, I should make a few comments here. Right, so there's one important thing that I haven't actually shown. I've claimed, but I haven't shown, which is that the way that you follow, if you deform this path in an arbitrary way, the result of the adiabatic evolution doesn't change. Okay, within this picture, the claim is basically that if your rule is that you're not allowed to change the ground state degeneracy, throughout step number 1, you simply can't turn on a J23 that would lift the ground state degeneracy immediately. So you basically are constrained to move in this plane, in this J13, J34 plane. That's why the area of this path is actually fixed. Okay, so you're not allowed to do that. However, as was mentioned last time, there's actually another parameter that I have to allow for, which is J14, that's kind of outside of this diagram. So that can vary in an arbitrary way during step number 1. The only constraint is that it has to be 0 at the beginning and the end of step number 1. However, it turns out that the result actually doesn't depend on that. Okay, and that I will not prove to you. If you're interested, I can outline how to show that. But so the result U12 is actually topological in the sense that it's totally insensitive to some small deformation of the path in Hamiltonian space. Okay, if you add any delta J of t to these different couplings, as long as in step number 1 gamma 2 is decoupled, in step number 2 gamma 4 is decoupled, and the last step gamma 1 is decoupled, okay, the result is going to be the same. Okay, so that's comment number 1. Comment number 2, okay, this is an actual representation of the braid group. So these matrices, this matrix U actually forms a representation of the braid group. Okay, more precisely, one should say that it's a projective representation of the braid group. Let me explain what I mean by that. So the braid group is defined on some objects which are ordered on a line. Okay, 1, 2, 3, etc. Okay, and you can braid consecutively every pair, every sort of nearest neighbor pair. So you can have braiding operations. So this is the U12 that we've described. You can have U23. Suppose you have many of these, so you can braid any pair. The 3, 4 here is not the same as the auxiliary Majoranas. It's an actual free Majorana. Okay, these are extra 0 modes that are not coupled to anything. Okay, and the braid group is basically the group of all the sequences of braiding operations that you can form, but it has certain constraints. Okay, so for instance, we require that if you braid 1 and 2, and then braid 3 and 4, these two operations commute. Okay, or more generally, if you braid J and J plus 1, and then you braid K and K plus 1, okay, if K is bigger than J plus 1, these two things commute. U, J, and J plus 1. Okay, this would be trivially satisfied by our braiding matrix e to the pi over 4 gamma a gamma j plus 1, okay, just because the two operators gamma j plus 1 and gamma k plus 1 commute. Okay, and there's another relation which has to be satisfied, which is slightly less trivial. Okay, so it's a statement about the following sequence of operations. Okay, so suppose we have 3 of these objects, 1, 2, and 3, and we first braid 1 and 2. Okay, and then we braid 2 and 3, and then we braid 1 and 2 again. Okay, so that's one element in our group. And we can have another sequence of braiding operations, which is defined by first braiding 2 and 3, and then braiding 1 and 2, and then braiding 2 and 3 again. Okay, so this is U12 times U23, and this is U12 again. This is U23, U12, U23. Okay, and what we want from this group is actually that every space-time diagram that looks like this would be the same as every other space diagram that you can get to by moving these strings around without tearing them apart. The result should depend only on the topology of the braid and not on its geometry. Okay, and the claim is that these are actually deformable to each other, as was explained by Giuseppe yesterday. It might, in the general case, it might be hard to tell. In this case, it's not so hard. You can imagine taking the strand of number 2 here and sort of sliding it to the right. You'll actually get the right-hand picture. Okay, so these two things should be equal to each other. And it turns out that our matrices actually satisfy that. That's a little computation you can do. Okay, but now there's one caveat. Okay, remember that our matrix U12, we could guarantee that it's e to the pi over 4 times gamma 1, gamma 2, only up to a phase. Okay, and this phase might depend on how we implemented the braiding. So really, what happens here is that this relation is satisfied up to a phase. Okay, the matrices are the same in the sense that they're proportional to each other, but there could be an overall phase. So this is sometimes called a projective representation of a group, which means that the matrices satisfy the group relations up to a phase. Okay, so using this discrete braiding of zero modes, what we really get is a projective representation of the braid group, not a real representation. Okay, so right, so I think I'm going to break here. So the two things I want to discuss before moving on to fractionalized Majorana's is right. So we saw that you can get a representation of the braid group using Majorana zero modes. Now we'd like the dream is to use these Majorana zero modes as qubits. So for that we need a set of braiding operations that would be universal for quantum computing. I'll demonstrate that these Majorana zero modes, as was mentioned earlier, are actually not universal. Okay, so that's part of the motivation to try to look for things beyond Majoranas. Okay, so some systems that would realize a non-abelian statistics which is non-Majorana-like. This is called Ising enyon, so non-Ising enyons. Now, it's after realizing that you can get Majoranas already in a one-dimensional system, essentially. So it's these superconducting wires. There's a natural question, which is we consider the wire which is essentially non-interacting. Our Hamiltonian was a quadratic Hamiltonian of fermions. Well, I mean, we can turn on arbitrary interactions. Can we get something which is richer than Majorana's just by turning on some interactions between fermions? So our Hamiltonian was schematically some quadratic part. Okay, we have this Nambu spinner, and this is some matrix. Can we add, say, quartic terms of this form? Are there extra topological phases that would give us some new kind of zero mode, which is beyond Majorana? Okay, I will argue that the answer to that is no. You actually, generically, you can only get Majoranas in one dimension and nothing more. To actually get something beyond Majorana, well, I mean, one example was already shown. If you think about phases of electrons in a 2D space, there's much more possibilities. The Reed-Rezai states are one example. They realize Fibonacci anyons, which are definitely beyond Majoranas. I'll describe actually a different route to get richer things, which is to consider two-dimensional states, but even abelian states, and introducing some defects in them. Okay, so this kind of generalizes the notion of the vortex in a P plus IP superconductor. The P plus IP superconductor itself is, in a sense, it's not a non-abelian phase, it's just a superconductor. Okay, but the defect in it, which is this vortex, carries some zero mode, which has non-abelian properties. I'll kind of generalize that notion to other states, like a Laughlin, abelian quantum Hall states. Right, and that's basically my plan for tomorrow morning. Okay, so now I guess we'll move on to the discussion.